This is Unit 8, Area and Solids, Lesson 8.4, Probability and Area. Probability and Area. Date, time, and location. Also, should be getting a parent supervising signature here, folks. Key terms. We're going to talk about composite shapes and probability. Talk about normal shapes, regular shapes, composite shapes, something called negative space, part over whole, and notability. Normal shapes are just shapes of singular shapes, normal shapes, things like triangles, circles, trapezoids. Then you specifically have regular shapes. These are shapes that have all equal sides, all equal angles. One implies the other automatically. So if you have all equal sides, you automatically have all equal angles. If you have all equal angles, you automatically have all equal sides. That's what the word regular. Now, we're going to talk about today something called irregular composite shapes. Composite means things that are made up of other shapes. So, for example, in this shape here on the left, it consists of a composite of a triangle and a semicircle. This shape here consists of a rectangle and a smaller rectangle. You can visualize that vertically, or you can visualize that horizontally going this way. Either way, you're going to end up with two distinct rectangles. So that is a composite shape. Now, there are two ways to find composite shapes, something called positive and negative. Composite shapes are a combination of normal and regular shapes. You need to learn to see the shapes as both a breakdown of smaller shapes and something called negative space. So there's two ways for you to look at the same image. This image, we can see it like this. Two smaller rectangles, and we can visualize it as horizontal rectangles, and we add those together. That's why this method is called positive. Or we could visualize it vertically, going this way. You're going to get the same thing. And once again, you'd find the area of both of these and add them. Okay, that's called positive. Now negative, because you're adding the area of other shapes. That's why we call this the positive method. Or you can visualize it like this. One giant rectangle, and then you're going to subtract out this negative space. Subtract out. That's why we call it negative. We're going to subtract out that negative space. So that's called negative. So let's do this first method. We're going to do it the same way both times. So taking a look here, I see that my length here is 3 and my width here is 5. So my blue rectangle is going to be, that area is 3 times 5, which of course is 15. I check for units. Feet squared. taking a look here. Be very, very careful. This area, length times width. The most common mistake here is you simply write 2 times 6 because your eyeball picks up that 6. That would be incorrect. Always physically trace the dimensions you're working with. Always physically trace the dimensions you're working with. Because yes, when you trace this, your brain registers that is 2. But this right here, when you trace it, you realize, wait a minute, that's not 6. Come up here. This whole thing is 6. From here to here is 3. Therefore, the actual length of this rectangle is 3. 2 times 3 is 6 feet squared. So my area here is going to be 15 feet squared. My area here is 6 feet squared. So my total positive area, and we're calling it positive because we're adding the blue and the green, and you get your total area, which would be 21 feet squared. That's called positive. You add up smaller shapes. Now, another way we could have visualized it is what's called negative space. Here, we find the area of this larger rectangle, which if you look carefully, that larger rectangle is 5 feet and 6 feet. And we're going to subtract this negative space. And we know going this way, just so you can see it, if this is 5 feet and that's 2 feet, that means this edge here must be 3 feet. Going this way, once again, always physically trace everything. This edge is 6. 6 from here to here is 3. So you can see that that edge right there must also be 3. So to get our negative space, 5 times 6 is 30 feet squared. We're going to subtract our negative space, which is 3 times 3, 9 feet squared, and we get the same answer, which is 21 feet squared. So once again, you need to be able to visualize both methods. Positive, smaller shapes add up to a bigger one. Negative shape, larger shape minus empty space gets you the other shape. That's a composite shape. We're going to do 2 more here, and you're going to do 1 on your own. Positive. We see here that we're going to add the area of the semicircle plus the area of triangle. Now, the area equation of a half circle is pi r squared, and it's half, so it's over 2, plus the area of a triangle. This is going to be a little tricky because it's base times height over 2. Problem is you do not have either of those right off the bat. Let's see what we do have. Here's the trick to the whole problem. See these hatch marks? That means all 3 of these are 36. So we see right now our radius has to be half of 36. So we just found the one thing we needed for that semicircle, which was the radius length. So our radius is 18. So we're going to go 18 squared times pi over 2. We'll work that out in just a moment. Over here, our base of our triangle is 36. This height here, look very carefully. That height smacks this right in the middle. We know this is 18. And if all three sides are equal, all three angles are equal in this case. So that would make this 60 degrees, 30, and 30. And we got ourselves a 30, 60, 90. Short leg root 3, short leg times 2. Now, we could use SOHCAHTOA if you want to do this in decimal form. But since it's 30, 60, 90, I'm just going to do this in exact terms. This is going to be 18 root 3. So my height here is 18 root 3. $18 squared divided by 2, and I get 162 here on the left, 162 pi plus 2 goes into 36 18 times, so that's 18 squared again. 324. So it's 324 root 3. Now, if I wanted this in exact terms, exact meaning no decimals, I would actually have to stop right there because you cannot add 162 pi and 324 root 3 because that radical is not the same. So this legitimately would be your final answer if the term asked for exact. To get the decimal version, you would simply multiply this by pi, multiply that by root 3, and you can get a singular answer. And if that's the case, it would use the term approximation, which means a decimal. Positive, we added something. Negative, find the area of the shaded region. The inside shape is a rhombus. Each vertex is 1.5 units from the side, so that each vertex is 1.5 units in from the side. Okay, to get this shaded region, we are going to have to use what we call negative space. We're going to find the area of this entire rectangle. And then you subtract the area of the negative space, which is going to be the rhombus. Now, the area of the rectangle, of course, is length times width. The area of the rhombus is going to be diagonal times another diagonal over 2. Let's take a look here. Always physically trace everything. Your length And your width are 6 and 10 here. So of course we get 60, check for units, we don't, it's going to be units squared. That's the entire green rectangle. So going this way, we trace that diagonal, which if you look very carefully, we're going to trace it very carefully. I'm going to bring it real close here. Watch the little finger thing here. From here to there is 10. But we only need the length of this diagonal. So we're in 1.5 on one side, 1.5 on the other. You add that up, that's 3. So 10 minus the 3 gets me that one diagonal is going to be 7. My other diagonal going this way, the whole thing, of course, is 6, but you go in 3 on both, 1.5 on both sides, which is 3. So that means the length of that diagonal is going to be only 3. So 7 times 3 over 2. Our area of our shaded region is going to be, of course, that's 60 minus 21 divided by 2, which is 10.5. So it's 60 minus 10.5. 60 minus 10 is 50, minus 0.5, that makes the shaded region 49.5 units squared. That is our shaded region. That's called negative space. Now I'm going to introduce one final thing here called probability. Calculate the percent probability that a random point will be in the shaded area, so somewhere in the shaded area, compared to the entire shape. This is called geometric probability. Geometric probability is associated with the comparison of area and also the comparison of volume. Comparison of area, comparison of volume. When we do percent probability, it's the area of the potential over the area of the whole. In this case, the area of the potential is this shaded area that we found. The shaded area, which was 49.5 over the area of the whole, which would be the whole rectangle, which is 60. And we're going to round it to the nearest, the hundredths place. So we get approximately an 83% probability that any random point will be in the shaded region compared to the whole. Now I'm going to do one problem with you, and then you'll do one on your own. So we're going to find the probability that a point lies in the shaded region. So the shaded region would be this region, percent probability, compared to the entire, this is a typo, should be circle here, compared to the entire circle. So first off, we need to get the area of the shaded region. Probability is simply part over whole. to get our shaded region here, we're going to find the area of the circle, and we're going to subtract the area of the square. Now, the area of a circle, of course, we know is area equals pi r squared. Now, a square, of course, you think side squared, and that's perfectly fine, side squared. But there's a shortcut here. A square qualifies as a rhombus. Remember? When the diagonals make a right angle? And it's actually a little faster here because our diagonals we already have. Area equals one diagonal times the other one over 2. That is the area of a rhombus. Now, if we wanted to find it, if this whole length is 32, this would be 16 root 2, but we're not going to go there, okay? So our area of the square is going to be one diagonal, which is 32, times the other diagonal, which is 32 over 2. The area of our circle is going to be 16 squared times pi. Now, because we're subtracting to get the shaded space, we have to get our decimal here. So first off, I'm going to go 16 times 16 times pi, 804.25. So our total area of the circle is 804.25. Now come over here. We're going to do the 32 squared divided by 2. You get 512. I'm going to subtract these because I'm ultimately looking for the shaded space. I get 292.25. That's the shaded space. So our part here is our shaded space, which is 292.25. Our whole was the whole circle, which was 804.25. Now I want the percent probability that a random point is inside the shaded region compared to the entire circle. So I simply take that 292.25 and I'm dividing by 804.25, part over whole, and there is a 36% probability that a point will land in the shaded region compared to the area of the entire circle, a 36% chance. This page you're going to do on your own. Pause the video, read the instructions, do the work, restart. Welcome back. It says, find the area of the shaded region, find the percent probability that the shaded region compared to the entire square. So the shaded region is going to be the area of the square minus 4 of the circles, of course, minus the 4 circles. So our square is length times width. That's 36 minus, here was the trick to the entire problem. If that is 6 this way, our diameter is 3, which means our single radius is 1.5. So to get one square, one circle, that's going to be 1.5 squared times pi, and then times 4, because there's 4 of them. So 1.5 squared times pi times 4. You would get 28.27. We subtract that from 36. Our goal is to get that shaded region. And we get 7.72 is our shaded region. 7.72 is our shaded. To get the percent probability that a random point is in the shaded, compared to the entire circle, we do shaded. Over the whole, which is 36. You divide, because it's part over whole. So there's our part over our whole. You should have gotten approximately, there is a 21% probability that a random point is inside the shaded region compared to the entire area of the entire square. Very important you go back, take the time to verbally recap what you've learned today.